Welcome back to ECE 441A, 541A. This is our last class meeting. We will meet one more time this semester, which is in a week for the final exam. That's scheduled for the 17th of December from 8 to 10. You have several things that are needing to be finished up before then. The main thing is studying for the final. But before that, you have two homework assignments that are due today, 9 and 10. And if you haven't already turned in lab number 3, that is due this evening also. And if you're in 541A, you have even one more thing, which is your project to turn in, and that's due today. Well, one more thing that's due, if you haven't done the teacher course evaluations, that's due today also. So I would appreciate your feedback on that form or on that instrument, since you're learning all about feedback and we can use it to correct things. That's how I would use your feedback to adjust how this is taught the next time around. Relative to the plan, we have a week to get ready for the final, and I've scheduled several days of 2-hour blocks. I guess it's every day between now and then, except on the weekend. I need to kind of get caught up with my other tasks on the weekend, but today it's the normal 2-hour slot right after class from 9 to 11. Thereafter, it's sort of different. We've never had scheduled hours on Monday and Tuesday. I've introduced a couple of those. There's also a change in the Thursday and Friday office hour time slots, and I tried to put those at a consistent time. Those are at 2 to 4, which will be tomorrow and Friday. I'm trying to remind myself what today is. Today is Wednesday, the 10th. It's the last day of class. And then Monday, since I have a class, another final exam on Monday in another class, that time slot is switched from the normal 2 to 4. It's now at noon to 2 on Monday. But all the others are 2-hour times. Well, they're all 2-hour time slots, and try to remember those, or these notes will be available on D2L if you need to remind yourself of when those are. And hopefully I will remember those also, but those will be in my office, 523 in the ECE building. Today, what I want to do is, I think when I was finishing up last time's lecture, I said, oh, I'll give you some controller comparisons or the plots after the fact, and I thought maybe we would just go through those together. I think it would be easy, or maybe more helpful for me as we're working through those, to answer your questions if you do have questions about what's going on or what's happening relative to these design concepts. But before we talk about the controller comparison, I want to just remind you of the final exam process, which will be consistent with what we've done so far this semester relative to the process for the final. But our controller comparison is what we will spend, I think, some of the time on, or the first half of the time, the output feedback design approach versus the full state feedback design approach. Then we will actually let you in on how to realize these controllers, how to build those if you wanted to. How do you build these transfer functions G sub C of S? And you can do that passively. That means R, L's, and C's. Or for this discussion, just R's and C's, resistors and capacitors. Or how can you do it actively? And typically when we need some gain in the system, we are going to have some active components. We'll just go through some of that in terms of some pictures of circuits dealing with RLC or RC circuits, maybe some op amps for the active, and then we will talk about controller types, when we might want to make this decision as to the type of controller that we need to use or want to use, And if we have time, we'll talk about how we might actually put integral control into this full state feedback design technique or approach. That's where we're headed for today. Getting into that material, the first thing that I want to go over then is this final exam process. The exam is comprehensive, and it will look more like exam number 3 than exam 1 and 2 in terms of number of questions. And those will be then essentially pick 15 topics out of the course of the semester, and that's what it will be. Now, some people are saying, is there going to be material or emphasis on the material since exam number 3? Well, we have covered a fair amount since exam number 3. We've talked about Bode plots. That was actually exam 3, but then we talked about controller design with Bode plots, and we've done full state feedback design. So that's going to give us, we've maybe looked at gain margin, phase lead, and phase lag with Bode plots, full state feedback. So there's at least a fourth of the final exam, which is consistent. This is our 4th exam. So it's now a comprehensive final, but you can see how this could sort of just all roll downhill. We start at the top of the hill with our model, and now you just build from that. You can analyze how it will behave. Maybe you're not happy with the way it behaves, so you build a controller. And how do you design that controller? That's based on meeting certain design specifications. Question. Is there a practice exam? Not explicitly. So your practice exam will be your homework since exam 3 and all the previous exams. So you won't have that opportunity, but we will hopefully help you a little bit in today in talking about these controller designs to get you ready for the final exam. But that means you need to focus maybe a fair amount of your attention on how do you design controllers and how do you look at gain margin and phase margin and enhancing those or changing those relative to a Bode plot. Yes? The question was, am I going to provide you with semi-log grid paper on the final exam? I think that's the question. And I think I want you to spend half of your time actually drawing your grid. I think that would just be enjoyable for me to sit up here and watch you sweat that out. No, I think if you need that, I'm going to hopefully have some semi-log paper embedded into the final exam. That's the idea. And you then need to understand how to place your poles and zeros or your breaks and bends, how to identify the appropriate frequencies on this semi-log paper and know where those tick marks need to be or are located in this semi-log paper. Other questions? So here it is, 4 sheets of notes. You can bring in an additional sheet, so you could have as many as 5 sheets with you on the final, one of those being a photocopy of the Laplace transform tables. Something to write with. A calculator is allowed, but you can't have your cell phone or computer as your pseudo calculator. No, I forgot my calculator. Can I use my cell phone? Nah. So you'll just have to use your mental calculator if you forget your calculator. So remember your calculator. Other questions on the final exam. It is in a week. You have 1 week to prepare, and you have some additional office hours available to you from now until then. Every day of the week there will be office hours if you want. And most of those will be from 2 to 4, but we have the typical ones today. That's locked as normal, but then it changes for our normal Thursday and Friday office hours. And hopefully this straddles final exam time so that I didn't pick one block that if you had a final from 2 to 4, there's no way you could come see me. At least you can have a 30-minute window, I believe, at the worst. And maybe you can have the full 2 hours. But I'm hoping now you're starting to get all of this material clean or clearly positioned in your brain or in your head as far as how it all fits together. Questions on that? Let's now talk about this controller comparison. And as I said, I was going to give this to you offline, and then I said, well, that might not be as effective as having you here to ask me questions as we walk through this. So here is the system, and it shouldn't surprise any of us that we can model that in the time domain or the frequency domain. And this is the same system we had last time. It's a second order system. You could tell me immediately what the eigenvalues of that system are, I hope, the open loop eigenvalues. Since it's an upper triangular matrix, you now know that those eigenvalues are on the diagonal in your system matrix A. Those are consistent with the poles of your open loop system. The poles are at the origin and at s equal -1. Those are the values of s that cause the denominator to vanish, and the relationship between the two representations are g of s is equal to c si minus a inverse times b. And if you had g of s, do you remember how to maybe get the state space? Well, now you could just put it into a standard state space representation by identifying the coefficients in the numerator and the denominator of your transfer function, or you could start going through an all-integrator block diagram. And if you do have an all-integrator block diagram, how do you build up a state space representation from an all-integrator block diagram? Algebra, you label the states as the outputs of your integrators. Then the inputs of those integrators are your x dots. And now you have an x1 dot, an x2 dot, and you simply write equations based on what's x1 dot equal to in terms of the other x1s, x2, x3s, and u's. That's how you can write or create a state space representation given a block diagram, an all-integrator block diagram. This should be very comfortable. Now let's say that we have the design specs that we talked about last time. We want a steady state error of 0 to a unit step. Is that going to be difficult to achieve? No, because this system is a type 1 system. That's going to guarantee if we can keep the closed loop system stable, we will have 0 error due to a unit step or a constant. Any constant input, our system will be able to track it. If you wanted to find the error due to a unit ramp, so now I'm sort of, this is not really a design spec, how can I sort of keep that separate? By saying a question here in this cloud. Everything's in the cloud now, so I'll just send this question to the cloud. Here's a cloud question. What would be the steady state error if this system was stable in the closed loop and we put in a unit ramp? So I'm sort of going off the script, which is maybe dangerous, but I'm trying to get you thinking about the final exam and how you can now ask different questions relative to the final. Do you remember what the steady state error is in terms of gains in your system equations? if you had a type 0 system, oh, now I'm really getting off script. So again, this is in another cloud. I don't know if this is a Cumulus or a Cirrus, but it's some cloud over here. It's a type 0 system, which isn't our system at all, is it? What's a type 0 system? Now we do not have any poles at the origin, do we? If we had a type 0 system, our steady state error due to a unit input would be 1 over k sub p, where k sub p is your DC gain of your system. Do you remember that formula, or could you derive it? That's what you need to be able to do by the final exam, is you would identify your error location in your closed loop system, and it ends up being now this 1 over 1 plus k sub p, where k sub p is your position gain constant. Do you remember some kind of gain constant for the steady state error due to a unit ramp? Now that I've prefaced it with this left cloud, what's the right cloud expression? Do you remember? It's now not 1 over, so this is our position gain constant, k sub p. We also have a k sub v, our velocity gain constant, and that's because we're now hitting it with a ramp. Position is when we have a constant. Velocity is when we have this ramp. That's now this 1 over k sub v. And then if we had a parabolic input, we might have, or an acceleration input, then we might have a 1 over k sub a. All these others now start looking like 1 over k sub a if we put in a unit parabola. Now, what is k sub v relative to our system? Is there a formula for that? Oh, and why didn't you guys wake me up? The limit of g of 0 as s goes to 0, there was no s in there, was there? So let's just do it that way. I was really just wanting to say the DC gain, g of 0, is k sub p. That's your position gain constant. What's k sub v? Do you remember? And if you have a controller in there, it would be sg sub c of sg of s. You would be enhancing your gain by your controller. This is what's in the forward path with unity output feedback. All of these are assuming unity output feedback and that your system is stable. In this system, what is the limit as s goes to 0 of sg of s? What would be your tracking error if we put in a unit ramp? And we didn't control it, we just used this g of s with a feedback path, a unity output feedback. So this would be in a feedback configuration, but we wouldn't introduce any more gains or controllers. What is k sub v for this g that's in black up above? That's just 1, isn't it? The s's cancel, and we let s go to 0. We have 1 over 0 plus 1. So we have a k sub v of 1. Our error would be 1. And if we now had a unit ramp, oh, now I have to expand my cloud. But it's raining in California, I think, or planning to. So the cloud's getting bigger. But we might have a unit ramp, and now our response might look like that, and our steady state error that we said is now 1 is this tracking error between where we want to go and where we actually are moving. Is that clear? That's our air steady state. And I've put this squiggle in just to represent a transient. We have some transient interval before we get finished with the transient and we reach steady state, but once we've reached steady state, now we're tracking with an error of 1 for this system without adjusting the gain at all. So these were clouds that were just sort of off-script discussions. So when you start looking at the notes and you're going, well, this system isn't a type 0 system, you know it's not, right? Because it's in the cloud on the left. The cloud on the right does correspond to a type 1 system, which is what you have here. Questions on steady state air? That might be on the final. Hint, hint. Something dealing with steady state air, position, gain constant, velocity, gain constant, knowing how to do that. Here are our design specs. Getting back to the script, our design specs now are in blue. We have a steady state air of 0. We didn't get beyond that, did we? I got off script once we started talking about the steady state air. We now have a settling time of 1 second. What do you see when somebody gives you or says a settling time of 1 second? Do you now see a picture? Do you see an image? And what is that image? It's sigma, isn't it? Or it's an S-plane with a vertical line, and that vertical line is sigma into the left half plane. And now, depending on how fast or slow your settling time is, that impacts where that vertical line is or where your dominant poles need to be. And I apologize for those that are just listening. You're missing all my dancing up here with my hands. Yes, question? So now I'm not quite sure I'm understanding the question, but this unit ramp is the blue curve, and that's now what we are saying is our reference input. And if it's a unit ramp, then at 1 second it's at 1, at 2 seconds it's at 2, and at 3 seconds it's at 3. So at 10 seconds we might be at 9 if our transient has decayed. So you were thinking of the sawtooth. So if you were thinking of the sawtooth, which is a valid thought, now you hope that you hit the steady state before you reverse direction and go down. That's the only way you could realistically use this steady state accuracy discussion or concept if you were with a triangular wave. You would be assuming that you've reached the steady state pretty soon after you transition, start going up then down. Every time you make a transition, you're hoping you're already in a steady state before you get there. Here we're assuming this goes on and on and on that way. Is that clear? So I wasn't stopping at that point where I quit drawing my blue line. All right, now we've got blue lines, we've got vertical lines for sigma. What about percent overshoot? What do you see there? Yeah, you might see an angle, I might see a pizza wedge or a pie wedge. I see something, some angle in the S-plane that now if I want less overshoot, which way is the wedge moving? Is it getting bigger or smaller if I want less overshoot? My pie wedge. Am I getting a bigger slice of pie if I want less overshoot? No, right? I need it to be collapsing. I need my angle in the complex S-plane to be shrinking if I want less overshoot. All right, so now if we translate those design specs into closed loop pole locations, we now end up with this relationship between the settling time, which is 4 tau, it's a 2% settling time. And our tau is inversely related to sigma, and that's sigma giving us our vertical line, and that vertical line now is at 4 in the complex S-plane. We want our dominant poles to be to the left of 4 to get this settling time of 1 second. And if I said approximately 1 second, I'm probably wanting to be very close to that vertical line. I don't want to be way away from it if I want a 1 second settling time. I didn't say less than or equal to 1 second. I said approximately 1 second. If I did say less than, then you could move those poles further into the left half plane. The percent overshoot of 5%, now maybe you see this figure 5.8, or maybe you have the formula, this natural log of PO over 100 squared, that's in the numerator, that's divided by pi squared, boy I'm hungry today, pi squared plus that same natural log squared, and then you need to make sure you square root the whole thing. That will give you your zeta relationship with the percent overshoot. You remember what I was saying before was it was this guy. And I think I saw quite a few clear looks, but that's the formula if you don't use the figure 5.8. That's the relationship. We now have a 45-degree angle. We know that our horizontal distance is 4, our vertical distance is 4. We now want dominant poles at -4 plus and minus J4 to give us a 5% overshoot and a settling time of 1 second. If we put that into an output feedback controller, that's when we have unity output feedback, and G sub C is this forward block in our forward gain path. We have our plant, G of S, and now we're saying build a G sub C to achieve those design specifications. And now we have 3 parameters if it's a first order controller. We have a gain, K, we have a Z, and a 0 location and a pole location. And that's what I'm calling output feedback control, because we are measuring the output and feeding that back. That's what we're using to help us control the system. The other option, that's our first option for controller design, and here is our second option, full state feedback. And now I've drawn our system in an all-integrator block diagram form. That's now represented in black in this figure, except for the N that precedes it. But the U to the Y, that's our original system. And we don't have a lot of feedback behavior. We actually have a pure integrator. That's that integrator hanging out there by itself in the black diagram. We're now changing the system type with full state feedback. We've now changed the system type, so we no longer have unity output feedback, do we, in this configuration? We actually effectively are changing the dynamics of the system by introducing gains between the different state variables and the input U. And now we've completely changed the system type. Now it's a type 0 system for full state feedback. With 2 state variables, we now need, or we can find, 2 gain values, K sub 1 and K sub 2, to adjust the dynamic behavior. And we need to adjust N to change our DC gain in the system, because if we don't have that N, capital N, which in this case is a scalar, if we don't have that, we could be way off in terms of our steady state accuracy. We may say go to 1, and it may go to 0.2 because we've changed the behavior with k sub 1 and k sub 2. And we need to adjust the DC gain with this scalar reference input gain value, capital N. What we're buying, or what we're assuming here in this particular block diagram is actually the opportunity to measure each of our states, x sub 1 and x sub 2. Contrast that with this controller option, which is output feedback, and we are just measuring one variable, the output. But what are we also assuming? We're not getting a free lunch with this controller. What do we have to do in this system? That was pretty vague. But we have to build G sub C. We have to build some kind of system, maybe with op amps and resistors and capacitors, to build that transfer function G sub C. We have to create this compensator, this filtering mechanism that adjusts the air signal and then injects the appropriate input U into our system. We have to do that here in this full state feedback case. We simply have to change the gains, but we now have to buy maybe a second sensor to sense x sub 2 and then just scale that signal and feed it back into our system. So there's a lot of decisions or trade-offs that one makes relative to these controller designs. Are we clear with the distinction between output feedback and full state feedback? Homework 9 and earlier homeworks and homework 10, effectively. Homework 10 is full state feedback. Last time, didn't we design the compensator for both of these? I think we did. If you think about what we have for the output feedback, we had a pole at the origin and -1. We had desired poles at -4 plus and minus J4. And do you remember how we built our controller? To achieve our root locus, or make our root locus go through that triangle or those triangles. Now you know when you start with just 2 poles, it's not too challenging to modify that root locus. You're really preserving the general structure of the root locus, but you're just moving it over. If you cancel that 0 and now put a pole over here at -8, you now are going to have this branch coming in, this branch going out, and they then meet and go right through your triangles at -4 plus and minus J4. Meaning our G sub C of S has been specified at least by 2 parameters, just by plopping down a 0 and a pole. To obtain the gain K, we just use the magnitude condition to drive us to those triangles. And I think last time, didn't we calculate this? That ended up being 4 squared plus 4 squared, or 32, effectively. So that now our analog control, or our output feedback-based controller, was now this 32 s plus 1 over s plus 8. We also designed our full state feedback system. I'm going to sort of jump quickly into this. We had our A matrix, we had our B matrix, and then we had our K1 and K2, and we wanted this F matrix to produce, let's say, our desired polynomial, which, what was that? S squared plus 8s plus 32. Was that what it was? And that resulted in, if we did that with this F, I think our K1 was 7 and our K2 was 7 and our K1 was 32. Is that true? And our N, to get us, this is what I did after the lecture, but now in our U of t equaling minus kx of t plus n r of t, n equal to 32, produce the gain that we wanted. So that now we have U of t is minus 32, 7, x1 of t, x2 of t, plus 32 r of t. This is now our k, this is our n. So let's look at those relative to what they might do in MATLAB as far as the behavior. Or now let's look at our output feedback controlled system. We need to introduce our system. Let's call that system 1 is now a transfer function made up of 1, and then our denominator was s squared plus s plus 0. So there better be our system. Now we have our controller, which we can put in a transfer function form. That was 32 times the numerator, and the numerator was s plus 1, and our denominator was s plus 8. There's now our controller. And we need to put those together, combine those, multiply those together, and MATLAB is smart enough to be able to multiply those two transfer functions together when you just say multiplication. So there's our loop gain. We need to find our closed loop transfer function. So that loop gain is just the forward piece. We need to feed back our loop. That's our forward piece. We need to feed back in the feedback path a unity gain. That's the 1. Here is now our closed loop transfer function, CLTF. That's now this numerator pop factor over a denominator factor, and we could check the poles of the closed loop transfer function. And that's where we wanted them to be. Minus 4 plus and minus j4, and we've fixed 1 at minus 1. If we looked at the zeros of the closed loop transfer function, it's at minus 1. It's canceling that pole at minus 1. What we want to do now is really just sketch the step response. Not sure why I introduced a blank figure, but I did. So now let's just do the step response of the closed loop transfer function. Oh. Uh-oh. And there it is. And that's not in too bad of shape. We could right mouse click on that and say, well, let's look at what our peak time was. And we could then say, oh, there it was peaking with an overshoot of 4.32. We could do another right mouse click, characteristics, let's do the settling time, and then highlight that and maybe pull that down here. And we've settled close to 1. It's now 1.05. But that's pretty nice in terms of our behavior that we wanted, meeting our design specifications. Let's now look at the state space-based design. We had an A matrix, so I'll just actually do this in MATLAB rather quickly, I hope. Here was our system matrix. Here was our input matrix. And our output matrix was 1, 0, and we didn't have a direct feed-through matrix. I could put that in if I wanted to. Let me say D is equal to 0, just as a placeholder. I also know that the full state feedback gain matrix K was 32 and 7, and I can now have MATLAB do all of this calculation for me to get my full state feedback gain matrix, or my full state system matrix F is now this 0, 1, minus 32, minus 8, and I can now look at the eigenvalues of F, and those are where I wanted them to be, at -4 plus and minus J4. I can now actually build up my, let's say, state space closed loop transfer function. That's now simply SS of F, B, C, and D. This is now my closed loop system in state space form. And the nice thing, I guess, with MATLAB, or maybe it can be too easy, is it just keeps an object, and it could be a transfer function object or a state space object, and it knows. Now if I say step of SSCLTF, it will give me my state space representation. It'll give me my step response for that particular system. Let me just do it a little bit differently. Let's say that I now introduce a time axis, and I know from my earlier figure that I don't need to go any further, let's say, than 1.8 seconds in time for my time horizon. Let me now go 0, and I'm just going to go silly with my sampling rate, 0.001, and now let me go to 1.8. Now I want Y closed loop is equal to the step of, why did I say SSCLTF? That's not a transfer function. But anyway, I'm not going to correct it now. So I'm going to do the step for the time that I have given, and I don't want to see that necessarily yet in terms of Y. Let me now plot T versus YCL. And that's now my step response for my system, my closed loop system. Now I put in a 1 for my step. What happened to my output? Where did I go? Did I go to 1? No. What did I not incorporate yet in this particular, whoops, wrong mouse. Got 2 mice up here. I'm going to have to put a trap up here, capture one of those mice. Sorry. I'm just playing up here. You guys need to be doing the work. Where is this? Why is this not giving me a 1 as an output? I didn't put my reference input gain in yet, did I? My capital N. I need to scale my response by that capital N, or 32, So let me now do that. Let me introduce a new figure and say, let me rescale this. Let me say y closed loop 2 is now going to be 32 times. That's now my capital N, but I called this now this state space closed loop transfer. I don't know why I added that on, but I did. And now I can plot that in figure window 3, and now that looks more like what we wanted. Now I'm going to, I have 0 tracking error relative to this response. And that was because I needed to adjust my DC gain with this reference input gain value, capital N, which is right there. Before, in the first one, I actually had by default capital N equal to 1, and I went to 0.03 some place. So now I'm introducing that gain to get me the adjustment that I needed. And we found that gain value in earlier lectures. Questions on this comparison of controllers? What's the Bode plot look like for some of these transfer functions? Meaning, if I now looked at the Bode plot, you probably didn't hear that over the microphone. I don't think my microphone is that sensitive, but somebody got a little bit excited. Outside of class, I apologize. I thought everybody would be that excited in here, but okay, we're almost ready to get that excited, I can tell. But let's now look at the Bode plot for the compensated system. And did I call that L gain before? I need to do the forward path to get the Bode plot. That's what we're looking at relative to our stability analysis or margins. Is this system stable? And that's maybe hard to see. Well, you know it is because it went to 1. But what are our margins? Can you tell me what the gain margin and the phase margin are? What's my gain margin? Gain margin. So now my gain margin needs to be some gain value. What's my gain margin? How much can I crank up my gain and remain stable? So now to get the gain margin, we have to check what frequency do I cross my minus 180 degree line? Do I ever cross minus 180 degrees theoretically in this system? No, I just have 2 poles, don't I? My pole zero excess is 2. So I never go below minus 180. I do not have a phase crossover. So I'm not going to have a frequency that's going to allow me to check my gain at that frequency. My gain margin is infinite. I can continue to crank, and that's consistent with the 2 poles at the origin and minus 1 if you sketch the root locus. You could crank up the gain all you want. You might not like the resulting behavior, but it can go wherever you want. What's our phase margin? What's my gain crossover frequency? What's my gain crossover frequency? 10 to the 1/2. Isn't it close to one of those crosshatched grid lines? There's so many of them. Okay, look at 0 dB. Now I can't do this. I need a laser pointer, and I didn't bring that with me, and I'm not going to jump up there, and I won't. I can use my mouse here. Isn't it right there? So now I have to start at 1. That's 10 to the 0. 2, 3, 4. Isn't it about 4 radians per second, my gain crossover frequency? Now if I go down here to 4, 2, 3, 4, I'm now quite a bit bigger than 45, aren't I? I'm somewhere between 45 and 90 as far as my, and I could cheat. I could go back here and I could say, well, just let MATLAB do it. And so I did. What does MATLAB tell me? It says my gain margin is infinite. Yay, that's what we said. And our phase margin is close to 4. Our gain crossover frequency is close to 4 radians per second, and we have a phase margin of 65 degrees. So good luck with the rest of this class. We'll see you again in a week for the final exam. Good luck with your other classes, and maybe I'll see you in office hours, maybe I will not, but that's it for this class.